way, this way.
Morning, everyone. I hope I'm not giving anyone any sunburns with this thing. Quick show of hands. Who knows what a commitment scheme is? Raise your hand. OK, over there. Who knows what arithmetization is? OK, we're good. Who knows what a rollup is? OK, perfect, because we're only going to talk about the last one. You don't need the first two, because this is not what ZK should be about. We're going to talk about the fact that all rollups should be applications, and all applications should be rollups. So who am I? I'm Sylve. It's a weird French name. You're never going to hear a weirder name than this in France. I'm the co-founder and CEO of Hylé, the lean blockchain, and I'll be your host for this session. So the objective of this presentation is to explain exactly what kind of great affordances that we have, thanks to validity proofs and zero-knowledge proofs, to build applications. And they're very akin to building rollups, in a sense. So let's take a very concrete example set 6 years in the future, where you want to build what is called an on-chain game. An on-chain game is a video game where most of the logic of the game is running or is verified by the blockchain. But it's 2030, so you have some requirements. First of all, let's cover why you may want to be on-chain. You have the usual trifecta: censorship resistance, composability, and distribution, because it's 2030 and everyone has a wallet, everyone is on the blockchain, and it's way easier to do this than through PayPal. But you have some requirements as well. For example, it's 2030, so you're starting to fill yourself. Block space is not an issue anymore, so you do not want to talk about block data or gas limits. You also want something that's very low latency. You want the best of both worlds. And because the metaverse is hype again, you're actually using the blockchain for something extremely useful, which is you're gating the access to your game with an NFT. But now you run into another issue, which is, OK, because we actually have standards in 2030, you also want your game to be private. You don't want to share with your friends that you actually attacked their ships. So very naturally, you're going to want to use ZK. And you will write your POC in Rust, because that's the best thing that you have. And it's 2030, so now you have plenty of options: SP2, RIS1, and I didn't find any fun pun for Valida, Nexus, or Jolt. I could have maybe done like Jolt with a 1 instead of the 0, but that's for another presentation. So if you start to look at everything like this, if you build your application using a ZK VM and you execute it not on-chain but verified on-chain, it's starting to look like a rollup. Woo! OK, everyone is following. Everyone is great. So what's a rollup? It's very easy. You just have a state commitment that's on the L1, and everything else is at the bottom of the iceberg in this weird IC database, and you don't need it. The reason you don't need it is because we have these great things called validity proofs, and you do not need to execute everything on all the computers at the same time. You can only verify proofs of state transition. So you start from the state green, you go from green to blue, and all of that happens below the iceberg. That's where the magic happens in your Rust POC, et cetera, et cetera. The only thing that the blockchain needs to verify is the state transition from green to blue, then from blue to red. Easy enough? In 2030, we're going to have a lot of cool stuff, because hardware acceleration works. We can do many different things. First of all, you have, let's talk about hardware acceleration first. We have access to, let's take the green line, for example. So the green line would be, how do you generate your proof as a user? You either send it to your dApp, like the actual game that's going to generate the proof, and send it to the blockchain. Or you take the line at the bottom, which is you just send it to a magical proven market that's going to prove it to you and send it to the chain. Or, because you're feeling yourself and it's 2030 and you don't want your friends to know that you've attacked them, you're going to do client-side proving, that's the red arrow, and then you send that to the chain. 3 different options, and that's great because it's 2030. The future is still very similar to today, because accessing on-chain data is still going to be the same. Either you talk directly to the chain, or there's going to be an indexer that talks to the dApp and you're reading the dApp. Exactly like what would happen today. But there's one thing that's not going to change, and it's bridges. Even if we have great ZK and everything else, you're still going to have the problem that all of these different applications will be stuck on their own little bridge. These are supposed to be bridges. My CTO did the slides, so you can blame him for the drawing skills. So recap. In 2030, transactions are just proofs of state transitions. Your application is just a verification key and a state root because everything is below the iceberg, and you just go from green to blue. Users are able to choose a variety of options for their proof generation, prove a market, proving services, or even client-side proving because NoirCon is happening one floor below us, and Noir is great. You can do client-side proving using this. And chains, and that's really crucial, chains don't do execution anymore. They do not store data anymore. They're just guarantors of data integrity. And of course, everything remains trustless and decentralized because it's 2030. So far, so good? OK, let's go back 6 years to today. It's 2024, and you actually want to do that. How do you do it? Well, you can't really because you get hit with reality in the head. Super hard to do this for 3 different reasons. What we're trying to achieve here is to build a provable application. So your game is running somewhere, it's generating proofs, you have options to generate the proofs, and you send them on chain. You want your application to be a rollup. That's the goal. So these are the 3 problems that you're going to run into. It's extremely difficult to compose smart contract calls if everything is provable. It's very easy if everyone is on the same computer, like replace blockchains with servers, where everyone says, oh, we all want to be on the same blockchain. It's as if they were saying, we all want to be on the same computer. It's great, but there's only so much RAM and so much CPU space that you can use. So it would be much better if everyone was on their own little shard, but it's very difficult to compose. Second, proving time. It's quite difficult. If it's on the critical path, you're going to run into issues. And it's the same thing with parallelization. So let's go with smart contract calls. We're going to go through all 3 different problems right now. How do you compose proofs? Here, consider that contract calls are basically provable state transitions. So the option on the left is how we're doing it right now. Let's say that you have a ZK proof and a REST0 proof, and your application requires both of them. You want the ZK proof to assert the identity of someone, and the REST0 proof, for example, to prove that you won a chess game. Like you have a Rust library for chess, and you run it through REST0. The option that you have right now is to use recursion, which means you building a first lock, and then you put the lock into another lock. So you need to prove ZK inside REST0 or REST0 inside ZK. It's great, but it turtles all the way down. It means that if you change anything in either of these programs, the whole tower collapses. What we think should be the standard is what we call proof composability. Rather than do vertical proof composition, you do horizontal proof composition. You just have your ZK proof over there that says, I'm valid only and only if the REST0 proof is valid. And then you have the REST0 proof that looks at the ZK proof and goes, I'm only and only valid if the ZK proof is also valid. You just send both of them on chain, and they're verified atomically at the same time. You compose proofs. You do not need to recurse them for composability. Second problem, proving time and latency. So here, let's say that we're running an auction as a provable program. So you have a Rust program that runs an auction. And in order to interact with it, the user needs to generate the proof to run the program on their computer, generate a proof, and send it to the blockchain to place a bid. So what's happening here is the character on the left is extremely happy. And this is supposed to be the arrow of time. They are on the application, they generate their proof, but by the time they've generated the proof and sent it to the chain, the auction has ended. But the intent of what they wanted to do was right in the beginning, right before the auction ended, but their proof hit the blockchain after the end of the auction. So they're extremely sad, and it didn't work. That's the kind of problem that you're going to run into if proof generation is in the critical path of your application. So how do we solve this? By not requiring proofs to be on the critical path. Sounds pretty dumb, but we haven't seen a lot of projects actually use this. The way it would work is, and also solves parallelization, two at the same time. So we have 2 characters there. One has blue lips, one has red lips. These 2 guys want to send, OK, no, actually, let's talk about the problem of parallelization. So you remember this issue here where I would send my proof, and it was after the auction ended. Now you have the problem that is even worse, which is we have 2 people that want to do the same thing. So they both generate a proof, they send it to the blockchain, but the problem is These transactions do not conflict, but because they change the same tip of the iceberg, they conflict. So it would work if everyone was on the same computer, but remember, we do not want to be on the same computer. So you run into an issue of parallelization. Mina solves this, for example, by requiring everything to be sequenced at the application level. But this is 2030. Remember, we do not want this. We want this to be fully decentralized and trustless. So how do we do this? Well, we coined that pipelined proving. The way it works is it's a bit like going to the restaurant. You book a table, and then you can come in later and just say, actually, I've booked a table. May I sit? And it's a bit the same here. What you would do here is the person with blue lips would send a provable transaction to the chain. It's not proved at that moment. You're not generating the proof. You're just sending it over. This is, OK, here's how it works. And because the blockchain has the logic for verification, you can come in later, generate a proof for both of these transactions because you realize that they do not conflict, and you can move directly from the green state to the red state. Easy enough. And lucky for you, so right now, I've probably, if I've done my job right, I've managed to convince you that it's much better to run everything as a provable application, and you also have options. And the good thing is, you can do it right now, because that's what we're doing at Hylé. So this is the most French thing that we could find. I'm pretty happy about this image. So Hylé is a decentralized N1 blockchain that is optimized for this type of provable application. Think of it as a blockchain that does less stuff. Hylé does not handle execution. It's up to the application to decide which execution environment they want. Do they want something that is fully decentralized with different sequencers, or is it something, just an application that runs client-side? What Hylé does is that it sequences the provable transactions that we talked about before and handles state transitions through validity proofs. And obviously, we have all that good stuff of pipeline proving and proof composability that we talked about before. And so if you remember the diagram of all the little bridges where we were very sad because the applications couldn't talk, the great thing that you have by doing this is that you recreate the abstraction of a single world computer. Rather than having bridges, this just means that everything is running as a smart contract, but a provable smart contract. So we definitely see this as the future of decentralized blockchain in the post-ZK world. This is Hylé in the middle. You can have, on the one end, a completely permissionless on-ramp thanks to great projects like ZKML and ZKP2P. This thing would run completely decentralized on the user's machine and require client-side proving. You would have at the bottom, let's say, like a pooling market or a DeFi application that is running closed-source strategies, but is still manageable and trustless because you would create validity proofs of it. But this does not require it to be a blockchain. And then on the right-hand side, you would have what we call like a player decentralized type of game where it's running on everyone's computers. But the good thing that we give you is 50 shades of decentralization at the execution layer, but we still guarantee data integrity, trustlessness, and composability. So think of it as Coke Zero, but for blockchain, and the aspartame would be validity proofs. Thanks a lot for listening to my talk. I'm Sylve. We're building Hylé, the lean blockchain for provable application. I'll be at the booth for the rest of the day, and thank you very much for listening to my talk.
Thanks, Sylve. Amazing. I think it's a pity for people outside the room who missed this talk. Any questions for Sylve? Yes.
Would you mind leaving the slides on if people want to? Possible? Thank you very much. Some of you need some tan. I don't think you've been missing out on sleep.
Hi, thanks for the talk. You mentioned about the recursion that the whole tower collapses if one of the proofs, subsequent proofs, is doesn't work. But then isn't it just easy enough to, before you recurse multiple proofs, you just natively verify it, which should be very fast, and then do the recursion so that you are sure that the tower doesn't break?
Okay, I think I understand the question. You have many issues with recursion. I was talking with François from Argument, who has a very eloquent way of saying it. It's the gold standard for proof verification on Ethereum right now is 300K gas. People are not willing to pay more than this. What does this mean? It means that we have, on the one hand, super good proving schemes, Starks, ZK VMs. Like, we could be very imaginative in the type of proving system that we use. But the issue is we have to comply with this 300K gas limit. And that means that you can do like moon mass things and have the best proving systems, but it still has to be recursed into a gross 16 proof. And that's going to add a lot of overhead. First of all, latency. Depending on the size of your proof, this can take hours. The second is not even talking about the time to generate the proof, but you also have to batch them to make them like economically viable. So it means that it's as if you were, I like to think of it as you want to go to the airport and you have different options. You're late, so you would want to take like a motor taxi, but you do not have the option. The only option is to take a bus. So you take the bus, and it's great. Buses are economical. It means that you can have a lot more people on the road, but you can't go faster. That's the issue that you have with recursion as well. So to come back exactly to the question that you were asking, do you mind rephrasing it? I'm sorry, I got lost. It was...
I think it makes sense. My question was, you said there's a...
Oh yeah, can we verify it natively?
Yeah.
That's exactly what I'm talking about. So
Right.
yeah, if we have different proofs, like what we want to achieve on Hylé is you just say that the inputs to the different proofs are linked together. So think of it as rather than like an imperative programming system where you say, okay, here's what you want to do and tell me what's the output. We just tell you, okay, all the side effects are going to happen at the same time, and you resolve all of that at the same time. So think of it also maybe as like complex numbers. They cancel each other out at the end of the equation, but you still need them in the middle as like a useful abstraction.
Right. Yeah, makes sense. Thanks a lot.
Anyone else? Sylve, can you share a little bit about the design of the DA?
Wow. Who's responsible for that question?
Me.
So where are we going? We do not need to have execution. The only things that you're going to need are sequencing of transaction. You need to know which came before what. So if I quickly go back, there we go. You just need to know who came before whom. That's the first bit. And in order for everyone to, and then you're going to generate a proof for the state transition. But in order to generate the proof for the state transition, you need to have access to the data. You need to be able to generate that proof. So that's where the DA comes from. In our case, the good thing is we do not need to hold that data for very long. We can be quite aggressive. And it's a bit like the restaurant as well. You book a table, but if you don't come in and actually eat, your reservation is going to be canceled. It's a bit the same here. You can book your table, and that's going to stay on the DA layer of Hylé. But if you don't come in and actually sit down and order food, we're going to cancel it out. So we can be quite aggressive on the DA side, which means that the client can be very lean, very small. We don't have like massive disk requirements for this. We're talking about days at most.
I see. Because, for example, Avail is using KCG, and I know some folks, they're trying to use Fry to just reduce the latency and the cost. So just curious, what mechanism or approach will you take?
We're going to use the just dump it in the DB approach.
I see.
Because we don't need to have, we have very low requirements. So we may use data availability sampling in the future, for example, but in the beginning, this is not much of an issue for us.
Got it. And by the way, is 2030 an optimistic or conservative projection?
Well, it depends. Wait, where is it? There we go. No, it's not optimistic. It's descriptive.
Thank you.
Thank you very much, folks.
Oh, one more question for you.
Dan,
Yeah,
you guys
thank
can't
you.
get
Thank you
enough
for
of
the
me.
great talk. So I have a follow-up question on the restroom proof model you mentioned, right? So
I'm sorry, the restroom?
can you go back to the part where you have like two transactions coming in, but right? So this figures. I understand this transaction when they come in, they're like provable but not yet proved.
Yes.
So this might be a stupid question. So how do you handle like avoid double spending here? So what if, for example, yeah.
So the example here would be that let's say this is an auction. So the green person has 10 USDC in their account, the red person has 10 USDC in their account. And they're both placing a $10 bid. But then let's say that the blue person is also putting down another $10 bid. So the thing that happens before this red line over here is that we're not making, the chain is not making, Hylé itself, not making any commitment as to the validity of the transactions. Think of it as like the quantum world. Everything is possible. But then you need to, in order to actually settle these transactions, the prover is going to need to generate a proof. And that proof is a correct state transition from the green state to, well, actually, it's neither blue or red. It would be like another one. But in order to do this, they will need to execute the transaction. And so you will not be able to create a correct state transition proof because this would conflict with the state. The program would just go, you just need to run the program needs to run and work in order for you to generate a proof. So if you're trying to spend 20 and you only have 10, the program is going to say, nah, doesn't work. That means that you cannot generate a proof, which means you cannot send the proof here, which means that the red person with the red lips wins. So you don't, it's a bit confusing at first because the DA part doesn't tell you anything about the validity of these transactions. Before the proofs are settled, you as an application or you as a user, we work under the assumption that you know the program that is running. So you're able to look at the DA layer, like at Hylé basically, before settlement and say, well, if I take like this bunch of transactions and I dump them into my program, it's going to tell me what's true. But Hylé itself is more like a storage layer at this point. Did that answer the question?
You're too popular.
I'm gonna get kicked out.
Hi, do you have example of apps that have been built using Hylé that would have been significantly harder to build without it?
Yes, but I did not put it on the slides, unfortunately. So check out the Twitter here. We have a builder who built what they call a provable email game engine. So, you know chess? You can play chess via the mail. It's called correspondence chess because the notation is very simple. You say like E1, E2, etc., etc. The thing that you're able to do with this, like what would be really cool is like, can you play this with email? Easy. So the thing that that person wanted to build is that there's a whole range of games that are called like play-by-mail games, which you just play via the mail. And it's really funny. If you look at the Wikipedia page, they have a whole section about cost, and it's like $2 per turn, which really sounds like the problems that you have with on-chain gaming. So what that person wanted to do is, okay, I want to play between two players, just sending each other emails. And then I want to be able to assert that one of these players has won, like checkmate. So the way they wanted to do this, and that's why I took this example, is that they used ZK email as the audit trail and to assert the identity of the winner. And they used a Rust library called Shakmati to assert that like there's an outcome of the game, like someone has won. And so they proved that using REST0. The issue that you would run into if you were not using Hylé is that in order for everything to be verified at the same time, you need to verify ZK-email into REST0. Or you need to verify REST0 inside ZK-email. And that means that it's cumbersome, it's slow, and it also puts proof generation in the critical path of your application. So what Matteo did is, well, I'm just going to send these blobs to Hylé, and then I'll come in and prove them later. So it was significantly easier for them to use this between that. That's the vision that we have. Like, we like to think of them as more like the Switzerland of ZK. All languages are beautiful. Some of them have their strength. Noir is great for client side, but if you don't want to handle a Rust-like language, maybe you want something that's easier. So we don't want to like vendor lock in anyone into any particular language. So I actually had a good answer for that.
Great. Yeah, please go to the Hylé booth and talk to Sylve if you
I'm
have
getting kicked
more
out.
questions.
Thank you, folks.
Thank you, Sylve.